Right, y'all. I'll be reading a little bit of linear algebra. I have to catch up on my uh, homework. And we're doing some chapter 1, section 5 of this textbook here. So figured I'll give it a little look over. We had to do uh, vectors and matrices recently, which I'm pretty familiar with. Actually tutored a class that actually spent more time on matrices and such than when I took that particular class. Uh, It was a undergraduate class. I can't remember the exact type of class it was, but it actually spent a lot of time on matrices. A good refresher. So theory of linear systems. So this is 1.5. We developed a Gaussian elimination as a technique, finding a parametric description of the solution of a system of linear Cartesian equations. Now we shall see that this same technique allows us to proceed in the opposite direction. That is, given vectors, we would like to find a set of Cartesian equations whose solution precisely spans that. In addition, we will phrase in somewhat more general terms the observations we have already made about solutions to systems of linear equations. So we're going from a vector, and let me increase the size of the book. Interesting. It seems like we're starting from a vector. Now notice that this is a system of vectors. And from that, we're going to go to Cartesian that spans all of the vectors that we mentioned in the first part. I meant to put a K here, right? So A is a matrix, n by n. And we have two ways to interpret the system of equations. The system that they're talking about is AX equals B, or X and B are vectors. So it's saying if A1 to AM denotes a row, the row of vectors of A. Interesting. So it seems like this matrix is a matrix of vectors, if I'm understanding this properly. So A equals I wonder why they called the vector with a capital letter. It seems like they're saying this is one row, and A will go down to N, and this A here will be MN. M is rows and N is columns. Did I do that correctly? Actually, I swapped it. So it'd be M here and N. M number of rows, N number of columns. So this is the nth row, nth column, and A itself is a matrix. So what it's saying is A1 is this entire row. So I'm unclear about what the notation will be. This is this entire row of vectors. So perhaps this is really V. And A is V1 to V. M. So I wonder why they have M. M is the row. We shall see, I guess. So C solves AX equals B. So I'll show this more closely. B is a vector as well. So as an aside, we have a matrix. Let's say a 3 by 1. Then we have to multiply it by, for instance, a 1 by 3 will work. And the result would end up being a 3 by 3. So basically the numbers in the middle would be the same. And then whatever numbers are on the outside would end up being the outside of the new, the result of that. Maybe we can make this one orange. So common one seems to always go down. Like for instance, 3 by 2, 2 by 1. So then we'll end up with a 3 by 1. So it's saying C is a solution of A only if A1C, which is the first vector of the A matrix, equals B1, A2. This is a vector. It's odd that they make it a vector with a capital letter, but so be it. Dot C. I'm just taking it from my dot here. Equals B2. And AM dot C equals BM. I noticed that in this example, B is not a vector. So if you look at the book, A and C are in bold, making them vectors, but B is not. So it seems like they're making the matrix in such a way to where it ends up being a scalar at the end. It says C is a solution precisely when it lies at the intersection of all the hyperplanes defined by the system of equations. Right? So the previous result was the row vectors, saying the column vectors of the same A n by n matrix This would be AJ. This is a vector equals. Now, one thing I noticed, and maybe that was a typo, I noticed that this is a column. And as I have here, the columns will go from, a single column will go from 1 to m because there's m number of rows. This is an m by n. It has m number of rows and n number of columns, is my understanding, which is why this column goes from 1 to m, like in this example. So basically, one will be here, one will be there. But I'm still unclear why they have the row going to m. I suppose they meant to put an n there, just like I have here. I'll change that. The book actually has an m. It could just be that I'm misunderstanding something, but I'll see. But maybe that's a typo. I remember the last book we used in my, it's the last book I remember really reading was my differential equation book, my differential equations class, and that book had several typos. The professor even said that it had several typos. No, I'm sorry, not that book. Class was it? It was actually my uh advanced Cal 2 class. It was that book. My bad on the differential equations book. But yes, the that book has several typos. It reminds me even my classical dynamics book. The professor was saying, uh, he was correcting several typos. So both of them do have typos. I don't know. Could be just misunderstanding something, but I'll if something clicks. As my first quantum professor says before it's over. So this will be in Rm. Reason being because it's a row from a m by n matrix. The rows go down to m and j is 1, 2, all the way to m, giving it to n. Interesting. That's right, because as we saw here, the the values in the matrix go from m to n. And by the way, right, never mind on that. All right, so they say this observation is crucial, right? So it's saying the matrix product. I'll highlight my handwriting on this one as I write this out. The matrix product can be written as we have AX equals. I noticed they skipped some steps. At least it seems like they did, which is how, these books normally do. So I'll fill in the steps of what I'm seeing they're missing. So we have the A matrix first. A1, 1, A2, 1, because that's a second row. And I'll go to AM1 because we're in the first row, first column. So it looks like I can put a 1 here to make that balance out. So continuing with that front, let's see, I have A, it is still in the first row, the second column, so 2 will go there. This is the second row, second column, a 2 will go there. And I'll fill this one out just to show first row, third column. And this is, I can fill this one out as well. So this will be the mth row, second column. And why don't we call, there's some dots here. And this one will be still the nth row in the n column. And then we have a matrix, the matrix X. So, excuse me, the vector X. So the vector X, it'll have to have as many rows as this has columns. So it should go to n. Let me see if that's correct. Oh, see, I forgot to skip that part. But it does show, if you look at it, it goes to n. So I just don't like the fact that they skip steps, but maybe that's why it's for us to just fill in. So there's x1, x2, xn minus 1, and xn. So that's because when this matrix is dot product n, each one of these terms is going to go into a particular column and multiply down the row. Therefore, we have to have as many rows in the vector as we have columns in the matrix. So this will be A, and this will be X. So when I multiply that out, I'll end up with, now we're getting to what the book shows. So the 1 will go all the way to the left column over there. I have A11, A21, all the way down to AM1 plus, and the same thing, the second term will go to the second column. So we'll have X2, A12, A22, down to AM2, dot, dot, dot. We have X to the n minus 1, which will also go to the next column. I just wrote A13 in that one, and then just left the rest of them dots. And then we'll have the last column. It should be a plus, so some dots, then a plus. But then we have, I'll just write that column the same as well. It'll be AMN. I need to add a little bit more room for my XN. That's basically what they did on that step. Right? So we'll multiply that out. That's how they get the last line there, x1. And we have the first vector. They just put a 1 there for the first column. So it looks like they're taking the column number, putting that on the vector that's there, plus x2, the second column, plus x n minus 1, a n minus 1, plus x n a n, putting just the column term, right? The same thing, just the column term is coming down. Actually, I should have put that n minus 1 as well. 1 n minus 1, so that was a little typo. Easy fix. All right, everything looks good. So I definitely did some of part of this homework already, but this is actually this topic is one that's new to me, as far as the what do they call it again? I don't remember the name of it. The theory of linear systems. It was at the bottom of this page. That thus a solution C of the linear system ax equals b provides scalars. Okay. So C, A dot C is B. We know that a matrix times this ends up being the dot product. Basically, this was just a series of dot products. So it looks like they're equating the dot product between the rows of A and the new vector C with this system here. But there seems to be some detail I'm not seeing. Let me write the first line. A1 dot C equals A. Technically, this should be I'll just name it this. This would be A1 C1 plus A2 C2. He's using an example of an R3 plus A3 C3. And he's saying this equals B1, if that's A1. So I see. So then they go on in reverse with this line and saying B, so this is still a vector. I thought that dot product gives you a scalar. That's pretty odd. B, oh, okay, okay. So B, it's repeating the line up there, is A1 C1 plus A2 C2 and so forth, which is what they have here. But it is pointing out the result of the matrix dot product of vector equals B, which is a scalar, even though they wrote it as a vector. So it seems like we're still talking about a series of vectors, ironically enough. All right, let's check out this example, perhaps to clarify some things. And let me write this down. It says our second geometric interpretation of the system of linear equations. Our second geometric interpretation of the system of linear equations. A solution C gives a representation of the vector B as a linear combination. That combination is C1 A1 vector plus C2 A2 vector plus Cn An vector of the columns of the column vectors of A. All right, let's check this out. See if this example clarifies some things. Right, so we have 4 vectors, and I'll highlight the book while I'm writing these down. So B equals 4, 3, 1, 2. B1 equals 1, 0, 1, 2. B2 equals 1, 1, 1, 1. And B3 equals 2, 1, 1, 2. And it says we want to express the vector B as a linear combination, oh, I see, of vectors V1, V2, and V3. Okay, I see what they're getting at. So it's saying B equals, let's say, alpha V1 plus beta V2 plus gamma V3. We want to see if we can write B as a combination of those with a certain scalar that makes it correct. I notice they're doing something. The process is slightly different, but I want to see if I can solve it in the way I would like to. I'll see if I get the same answer. I noticed that I do matrices slightly differently than uh, the book form often. I don't know if there's a shortcut or a long way, but check me out and see how this works out. So B equals alpha, that's 1, 0, 2, 1, plus beta 1, 1, 1, 1, plus gamma 2, 1, 1, 2. And that all equals 4, 3, 1, 2. So I'm thinking of making these into a system. So if we were to do that, we would have 1, 0, 2, 1, 1, 1, 1, 1, 2, 1, 1, 2. The vector would end up being alpha, beta, gamma, and that would equal 4, 3, 1, 2. And using the notation that we had earlier, this is a 4 by 3, 4 rows, 3 columns. And this is a 3 by 1, 3 rows, 1 column. And as you can see, it does in fact equal a 4 by 1. So the system is working properly. If I was to write this out, and I've been wanting to practice making more room in my matrix so I can draw my numbers in between them. 2, 4, 0, 1, 1, 3, 2, 1, 1, 1, 1, 1, 2, 2. So all I have to do now is just do some raw operations to solve for this. So if I were, for instance, to uh, take row 3 minus row 1 and put that into row 3, and let me show my page again bigger, and row, and just showing detail what I had here. All I did was write these out with these scalars in front. And to put these into a matrix form, you just take out the column vectors and put them all in a matrix here. And then all of the scalars that we're multiplying them by becomes their own column. And whatever's on the other side of the equal sign stays there. Make that a different color to stand out. So that's all we did there. If I was to color code this, we have these here. We have these here. And this part stays in the back. That's all we did. And maybe this would look better if I didn't keep them connected like that. So, and I'll continue this with row 4 minus row 1 to row 4. And actually, I'm going to say 2 times row 1, since there's a 2 in the front. So I'll say 2 times row 1. So I have enough room to write this out. This is minus 2 times row 1. So minus 2, minus 2, minus 4, minus 8. And this is just minus row 1. So minus 1, minus 1, minus 2, minus 4. If I write this out again, I have 1, 1, 2, 4, 0, 1, 1, 3, 0, negative 1, negative 3, negative 7, 0, 0, 0, negative 2. Right. That is clearly seems like I must have wrote something wrong, because 0 doesn't equal negative 2. So let's see what I wrote down wrong. I have 4, 3, 2, 1. Oh, that's what I did. I swapped these numbers. Did I write it down that way the first time? Right here. I swapped these numbers here. This is a 1, 2. 1, 1, 2, 1, 2. So, and that's a good way to check a matrix, by the way. You know that 0 is not going to equal a negative something. So with that correction, I need to change my multipliers as well. So this will actually be minus row 2 and minus row 1. And this would be the minus 2, row 1. So let me erase all of this. So this is just minus whatever row 1 is. So minus 1, minus 1, minus 1, minus 2, minus 4. And this is minus 2 row 1. So minus 2, minus 2, minus 4, minus 8. Oh, wrong spot. Minus 2, minus 4, minus 8. So I'll just erase this line completely. So then we'll have 0 like we wanted there. 0, negative 1, negative 3. Then we have 0 like we wanted there, negative 1, negative 2, and negative 6. And what I want to do is now I'm able to get these 2 rows. I want to try to get a reduced uh, echelon form by eliminating these, which seems very convenient. I understand I'll still end up having, I see, I'll have the one in the front of it, add the 1, so that won't be good. But I can go ahead and add this row up there. So I'll say row 1 plus row 2 is still going to be row 1, row 4 that is. So plus row 4, minus 1, minus 2, minus 6. So that'll give me 1, 0, 0, negative 2, 0, 1, 1, 3. That stays the same. 0, 0, negative 1, negative 3. That stays the same. And 0, negative 1, negative 2, negative 6. I'm getting closer to, uh, I forget the name, reduced row echelon. I believe echelon form is any number is a pivot, and reduced row echelon form is only ones are a pivot. So if I have, say, 2, 3, 4 in the diagonal, that's row echelon, at least echelon. And if I have just ones, it's reduced row echelon. So I'm trying to get it to reduced if I can. So now I can take row 4 plus row 2, let that be row 4. So this will be adding plus 1, plus 3. So this gives us the same row for 1 and same row for that. That is the same. And now we'll have 0, 0, -1, and -3. And you can see that those are the same. So I'll just do this in one line and just subtract. If I was to subtract row 4 from row 3 and make it row 4, that'll zero out. Since those are the same, it doesn't really matter. So just in case, I'll show it for uh, clarity. So row 4 minus row 3, row 4. And so little is going to change. Let me copy most of it. The row 4 minus row 3, since they're the same, and becomes row 4, end up still having this. So that means that that's a free variable. And while I'm at it, I just multiply this times -1, and then I'll have positive on this row. Now, one other thing I can do, I can actually subtract minus row 3, or the proper notation, row 3, row 2 minus row 3 into row 2, and give me my last thing. So minus row 3, we have -1 minus 3, or -1 minus 3, we have 0 and 0. Right. So that will mean that, and it makes sense because this wasn't a variable. So we have alpha is -2, beta is 0, and gamma is 3. So let's see if that's the book solution. Yep, that's it. I do remember us going over that in class yesterday. So I do not remember a homework problem on this. So I think this is actually into the next homework assignment. So awesome. And that was the first part of that. So it looks like we ended up doing it the same way. It looks like they added this step here, which for some reason it confuses me to do this as equations. Probably if I just practice with equations, I'm sure I'll get comfortable with it. But I don't know. I just like doing it directly as a matrix. And you can see how they did the step we did here. Looking at my notes, they did the step where they made it into a vector like this. They added this step. But you could just as easily, and technically, I guess I did that part as well here. Uh, I just didn't rewrite it again as 4 separate lines of equations. I did the highlighted part there, but I didn't put it into a box of equations like that, which is unnecessary to me. And as we were saying, this is A, This essentially we have the ax equals b, and we were solving for the variable that makes at least the vector that makes that work. Right? For some reason it seems weird thinking about those variables as the x vector, but currently that's the understanding. So basically this will be orange, and we were solving for that to make this thing work, interestingly enough. And the book, at the last one, I need to put my mouse on a slower scroll. They did row operations as well, slightly differently than the ones I did, but we came up with the same answer. So they finalized it by saying b, the b vector, equals negative 2v1 plus 0v2 plus 3v3. And technically, this would be our answer. I don't know why they call it b. Hold up here. Oh, I see. I gotcha. So b is final vector, but that's what it's going to end up being when we get the proper coefficients for v. So our x is actually v in this case. V is for the general setup, and I mean x is for the general setup. V is specific, so v is our specific. And v would technically be in green. Let's see here. Technically, all the v's became our matrix. So our current professor said math is notation, and that's what's tripping me up is notation here, because technically all the v's became our matrix. These were the v's from up top. V1, V2, V3 put in as a matrix. And it's saying that, okay, B is just basically splitting those matrices apart. Okay, and we have to remember that when we multiply this in, this will go to the left column, this will go to the middle, and this will go to the right. I guess technically we can call this what? Variable answer. I'll call it little a. These are the scalars. Is going to equal v. And I guess technically, I wonder if this can be solved with like a equals b a inverse. I'm not interested in doing that at the moment, but I wonder if it could be solved this way. Pretty sure I'm going to get some kind of error in the calculator. I heard to try it out. My calculator is right close by. So I'll go to the matrix. I'll edit this first one, make it a 4 by 3. So I have 1, 1, 2, 0, 1, 1, 1, 1, 1, 2, 1, 2. Going back to the matrix. I'm making this one a 4 by 1, which is already there. 4, 3, 1, 2. And now I'm going to do matrix A, inverse, matrix B. Nope, that doesn't work. All right, well, we just make sure we solve it with row operations. And we solve for our variables or coefficients, our scalars. Then our scalars can go here that we solve for. Our V's go back where they belong. And our B is still what it is, equaling that last column. So simple enough. Oh, let me make sure I show you what I was doing here. So the vectors stay the same. It has become a matrix here. So the A vectors are the same. The matrix in vector form. We call in A the scalars, alpha, beta, and gamma, and B in yellow stays B. So simple enough. Awesome. I'll be back this week. I'll be making sure to do more quantum mechanics reading to prepare for my class in the fall. I've already started that last week, I believe it was. So you can check out that video. Make sure you like and subscribe if you haven't already, and I'll be back.